Hi everyone. In today's session, we are going to walk through five problems from chapter uh, 5 that cover one of the most practically important topics in hydraulic engineering, pump system in pipelines. So we will cover five progressively more complex scenario. We will work with a single pipe, single pump in a pipeline, and then move to equivalent pipe for parallel branches, then pumps in series, pumps in parallel, and finally branching pipeline. By the end of this recitation class, I hope you will have a strong command for system head curve approach and graphical method for finding the operating points. So the core concept for this use the core concept that we are going to use in this recitation class will be the same. Like we will have we need to write some energy equation first, and then get the system head equation, and then we will build a table of system head values for various flow rates, and we will also find system head curves that intersect form characteristics, which is our basically operating points. So before we jump, let me remind you of the key equation we will be repeatedly using. Like you can also source from the textbook as well, but I have written here just two equation. This is static system head, and this is classical equation static head, which is like reservoir A minus B or B minus A. So and HL is basically frictional force plus H minor. So let's start with problem 5.5.4. This is your classic single pump in a pipeline problem, but with a twist. We have to account for minor losses from the fittings. So read the problem carefully with me. So like we have the pipeline of pipeline that has diameter of 1.75 feet that conveys water from reservoir A to B, and length of pipeline is 13,800 feet long, and frictional factor is also given, which is 0.016, and water surface in reservoir A is 14.7 feet higher than that of B, and like we need to consider minor losses. So there are square edge entrance and exit, and there is also swing type check valve and two rotary bulbs. So our task is to find the flow rate, pump head, and flow velocity, and the characteristic for pump are we have the table. So like I draw the figure already. So here like A is 14.7 feet higher than this B, and length is also I have drawn, and like I just it's random things in the figure like check valve and two rotary valve that we need to consider. So like we need to let's start with finding the static head, mm, which will be like static head will be EB minus EA. So the elevation of B minus elevation of A. So elevation of B is 0, whereas this A is 14.7 feet. So that will give us minus 14.7 feet. That this negative sign tell us pump gets 14.7 uh, feet boost from the gravity. So now let us compute the frictional loss coefficient K. So like from the Darcy-Weisbach equation, HF is equal to K times Q to the power 2. This is like M, but I have already directly used 2 instead of M, and our value of K is 0.0252 times F times L by D to the power 5. We know the diameter of the pipe as well. We know this length of the pipeline as well. We know frictional factor as well. So basically, it's for English system, for SI unit system. Uh, we need to have slightly like there needs to be conversion, but it's Basically, it's for English system, not SI system. So that gives us a value of k as 0.339. So we will need this value of k when we compute this HF. And let's go to find the minor loss coefficient. So basically, we have four fittings to account for. Like one is square is in trans, that has value of ke as 0.5. Swing type check valve, kv1 as 2.5, and two rotary valves that give us 2 times kv2, which will be 20. And we also need to consider about discharge exit, that is 1. So when we sum up the k, we got like 24.0. So for head minor, so it is like it's summation of k times b square by 2g, where this b is equal to q by a. So we will be using this to compute the H minor in later case. So and system head is given as static head plus head loss. So basically this HL is equal to frictional head loss, frictional factor head loss plus minor head loss. So so let us now build the system head table. So basically we will compute the HF using the k to the power k times q to the power 2, whereas we will also need to compute the S minor. So we will use this formula. So because we know the value of q, and when we substitute this here, we can compute the H minor as well. And we already have this static head, and after we compute the static head, H minor, and frictional factor head loss, we will just add it to make a system head, total system head. So like this Q and HP, they are given. So first, since Q is 0, so HF will be also 0, because Q to the power 2, it's obviously 0. So H minor is also 0 for that case, because Q is 0. And so static head, it's minus 14.7. So that gives us a system head of minus 14.7. So now let us read for 5 and HP of 289. So that gives us HF as 8.5. And when we compute H minor, so we will put the value of Q here, and D of 1.75 also here, and like it's putting here, and we will compute H minor. And we know this HS is already known. So basically we repeat the same steps for up to like 0, 5, 10, 15, 20, 25 flow rate, and we will have all these system head in the right part of our table. So once we finish that, we also uh, need to find the operating points. So let us draw the uh, graph that will help us to find the operating point. So on this y-axis, I have drawn HP head pump, whereas in the x-axis, I have drawn flow rate. So, and this middle part, it's the operating point. And this red curve, it's system curves that we computed, whereas this pump curve, it's given. So once we have all these things, and here we can see that at 20 there is operating point, and maybe this has like HP of 124. So at Q is equal to 20, our pump provides 124 feet of head, and also system demands 124 feet. So they match. So that's our operating point. So Since our Q is known 20 and HP is also known, so we just need to find the flow rate, no velocity. So when we use this continuity equation, so we will have the velocity as 8.32 feet per second. So hence our overall answer are Q is equal to 20, HP is equal to 124 feet, and V is equal to 8.32 feet. Now let us start question number 5.5.7. So this introduces something new, like introduces parallel branches between point B and C. The water can take two paths. This is very common in real water distribution system. The key question is how do we handle this in our analysis? One of the approach we will be using this solving this problem is use the concept of equivalent pipe concept. We replace two parallel branches as shown in here uh, with a single imaginary pipe that produces same head for the same total flow. So we have the reservoir at HA is equal to 100 feet and as D, which is our like second head. So which is at 150 feet height. So our length of pipe AB is also given, diameter of pipe AB is given, and for this branch 1 and similarly for branch 2, all those value are given, and we can see here I have already written as well. And for CD, its length is given, diameter is also given, so frictional factor is also given. Our task is to determine the system flow rate, pump head, and discharge in branch 1 and so basically we need to find here Q1 and Q2 for branch 2, branch 1 and 2. So let us find the equivalent pipe for branch 1 and 2. In the previous recitation class also I have talked about this. So for finding the equivalent pipe for branch 1 and 2, so let us assume like for making numerical easy in later part. So we can use diameter of pipe as 3 feet and frictional factor as 0.02 to make consistent with this diameter AB and CD. So we will be using this formula like equivalent for equivalent pipe. So it will be equal to DE to the power 5 divided by FE times LE. Root under square root. So this is our formula that we are utilizing. So from this, our main intention is to compute the equivalent length of equivalent pipe. So that give us 652 feet when we solve that. And now, here's the beautiful part. Since all three pipes in series uh, are in series, like AB, AB, and this equivalent pipe and CD, they are in series, so we can add them and consider that as single length for pipeline between A and D. So that gives us 5792 feet. Why we did this? Because we can it can help us to compute the uh, system head easily. So let us build the system head table. So we know system head is given as static head plus HL and HS plus HF. Since the question assume there is no minor head loss. So again for HF we will be using these K, K times Q to the power M. M is 2, and we also need to use G, which is 32.2 feet per second square. So when we compute the value for K, we will have 0.012 because like this is constant and this is frictional factor and this is length of equivalent pipe and this is diameter which we have assumed as 3. So now let us compile all those value in table format. So since this Q, HP, they are given, we just tabulate. For now, ignore this red circle things. I will explain that later. So Q is given, HP is given. Our aim is to find HP, HF, which is which can be computed from this K times q to the power m, and h minor is negligible, we can ignore that. And hf, like it's basically hf is h static head is equal to hd minus ha, which is equal to 50 feet. And this final system here is combination of hf plus h minor plus hf static head. So similarly, for all the Q and HP, I computed all those value. And for this headlighted part, I will explain with the figure or graph. So once we plot all those SP and flow rate, so that intersecting point here at here, it will give us like when we go down here, it will give us 13.5, whereas when we come here like in the horizontal section, it gives HP of 52.2. So that's how we get this. So now we have operating point and branch flows. So we need to find the flow rate for Q branch 1 and branch 2. So like head loss across BC will be equal to HF BC will be equal to, this is constant, and this is frictional factor, this is length of equivalent pipe, and this is Q we computed just now, and this is diameter, and we will have HF BC is equal to 0.246 feet, and we know that HF head loss for equivalent pipe is equal to frictional head loss for branch 1 and branch 2, they all are equal. So what we can see, what we can do is like let us use like HFBC1, which is 0.246, and when we compute that, like there will be unknown of Q1. So when we do computation, we will have 12.5 CFS. And similarly for branch 2, our Q2 is unknown. So we are, because like length is known, diameter is known, frictional factor is known, we will just use Darcy-Weisbach equation here to compute the Q2. And like we computed Q1, Q2 as well, and it's all for question number 2, which is. So now let's go to question number 3, which is 5.6.2. It's about two identical pumps in series. So let us read the question first. Like a 1.5 feet diameter pipeline conveys water from reservoir A to B. I have also drawn the figure for simplification. And B is above A by 196 feet, and the length of pipeline is 13,800 feet. Diameter of pipe is already I talked, and Darcy-Weisbach friction factor is also given, which is 0.02. And it also asks us to neglect the minor head loss, and we need to compute the flow rate and energy head added to the flow by each pump if two identical pumps are used in series. So here is pump characteristics, which has given like Q and HP. So here's the key principle for pumps in series. The heads add, but the flow stays the same. Think of it like two people pushing a car uphill together, one behind the other. The car moves at the same speed, but they can push it up stiffer hill. So same pump rate through both pumps. Total pump head will be equal to 2 times HP for identical pumps. Each pump handles the same Q but contributes half the total head. And we know this, and we know HF is equal to K times Q to the power M. M is equal to 2. And we know how to compute K. So we can compute from this formula, and we get like value of K as 0.916. That give us like HF is equal to 0.96. So now let us build the system head table. Build this system head table. So in our table, we list 2 HP as the combined pump curve. Was how the system head curve rises more stiffly than before because K is equal to 0.916 compared to previous. In the second question, we use K as 0.339. In the smaller pipe diameter makes a huge difference. So now this is given, HP is given, and we just multiply by 2, and this HF we compute by using above formula. H minus is negligible, which is 0. HS is when we compute energy head, we will have that static head, and this is the summation of HF plus H minus plus static head. So this help us to find the operating point. So we can also see in the HP and system head, pump head and system head, there is common of 402.1 and 402. These are close. So by seeing in the graph version, we can see here the HP intersect at 400, and here like its Q is at 15. So it's same. So we are done with the question number 5.6.2 as well. Now let us move to another interesting question that has two identical pumps in parallel. Here the question flips the concept, like instead of pumps in series where heads add, we now have pumps in parallel where flows add. Same head but more water. So let us read through the question first. The question has given us the diameter of 2 feet and length of pipe as 3000 feet, and we will be using Hazen-Williams equation, Hazen-Williams coefficient of 100, which help us to connect two reservoirs, and like the two pumps are connected in parallel for moving water through the pipeline from reservoir A to B. HA has head of 840 feet, whereas HB has head of 921 feet. So this question has also mentioned to ignore minor losses and find discharge in pipeline and pump head. So importance, one of the important difference here is use of Hazen-Williams equation instead of Darcy-Weisbach Darcy friction factor. So for computing frictional factor, computing head loss caused by frictional factor, we will be using the same formula like K times Q to the power M, but the value of M will be changed, which is equal to 1.85. You may confuse on this. Take note on this. Uh, Whereas K is computed differently by using Hazen-Williams equation. So that will give us 4.73 times L. We have a length of pipeline, and we know the diameter as well, and we know C as W as well. So when we put the values on this formula, we will have value of K as 0.968. So before we move down, like I already mentioned, pumps in parallel rule, it's like total flow is equal to 2 times Q per pump. It's for identical pump. So let us build the parallel pump plus system table. So total system flow Q total will be 2Q, and system head will be equal to static head plus HF. That gives us this static head 81 plus this K times Q total 1.85 power. So here we are not doing anything different. Like this is Q is given, HP is given. Instead of directly computing the from the original pump characteristics, we will be using this 2Q value for computing the head loss due to frictional factor. That's one of the difference here, and H minor is negligible 0. So HF system head we can compute by that. So basically it's like this, computing all those things, and when we plot that into curve, we will have like this HP and Q meets at this break point, and when we like see in horizontal, HP seems 200 feet, whereas Q seems 47 cubic feet per second. Now let's move to question number last, fifth one. So this is the most complex problems that we are dealing today. We have a pump feeding water from reservoir A to junction, and from that junction the water is split into two pipes, pipe 1 and pipe 2, that goes to reservoir B and C at different elevation. This is branching system, very common in real municipal water supply system. The challenge is that water splits at the junction, and we don't know how much uh, goes to each reservoir. The total flow depends on the pump, and split depends on the individual pipe resistance and reservoir elevation. So since we already have drawn this system here, so it the question asks us to find the discharge at each pipe, here in this pipe and in this pipe. Now let us compute K for each pipe. Since we know the dimension of the pipe, length, diameter, and there is also given of Hazen William coefficient is also given. So from that we can compute HF, head loss due to frictional factor, and M is also given. So for K1 it will be equal to 2.13. And similarly for pipe 2, when we use same formula, head loss caused by frictional factor will be equal to 4.27. And now let us write the system head equation. For pipe 1, static head 1 will be equal to HB minus HA 8 meter, whereas for pipe 2, HST static head will be equal to 12 meter. So like I mentioned, we can compute the head loss caused by frictional factor for pipe 1 and pipe 2 using this formula. And similarly, for computing the system head, it will be equal to this static head plus HF1 for pipe 1, and for pipe 2 it will be equal to static head for pipe 2 and head loss caused by frictional factor at pipe 2. So let us tabulate all those information. Q is given, HP is also given. We can compute HFN, HF1 and HF2. So by using this formula, and like I already mentioned about this system head for pipe 1 and system head for pipe 2. This will be crucial for finding the Q1 and Q2 in later part by using this formula. So once we have Q1 Q and HP, we can compute HF1. So this is just you can look how I did. And let us move to another step where we will be computing the Q1 and Q2. Before that, like total flow rate of the system will be equal to Q1 plus Q2. So since we know this system head for pipe 1 and pipe 2, we can compute Q1 and Q2. And obviously it is the combination of Q1 and Q2. So after computation for HP30, we will have Q1 of 3.5 and Q2 of 2.2, and total Q system is equal to 5.7. So to make visually appealing, so I have uh, here the curve for showing system head curve, pipe curve, and pipe 1 system curve, and pipe 2 system curve. So this green line indicates pipe to system curve. This blue indicates pump curve, whereas this purple indicates system head curve. And from the figure and from this operating point, we can compute the value for flow rate. Like for overall system, Q system will be equal to this 4.2. And for Q1, it will be equal to 2.7 cubic per second. And for Q2, it will be equal to 1.5 cubic meter per second. Whereas in horizontal section, head pump will be equal to 21 meter. So let's wrap up with the big pictures takeaways from today's session. So before we begin solving this kind of problems, first we need to look problems carefully and identify the static head, and we also need to consider about the unit, and we need to consider about like think about whether the pipeline system is in series or parallel, whether we need to consider the minor head loss or not, and we also need to distinguish between Darcy, Weisbach, and Hazen Williams as well, because they have two formula for computing the friction loss. And we also need to take care about the equivalent pipes, and we can always verify our system whenever the like we can always verify after finding the operating point. Does like Q1 plus Q2 equal Q total? Does the pump head equal the system head at that flow rate? Did check catch calculation errors immediately, and we can solve confidently as well. So that's it for today's session. So